So we've gone through essentially all the key angles, but let me draw below essentially a summary so that we can have a better way to remember all of those. So I've drawn this unit circle just a little bit bigger since we're, in this case, only really concerned with this first quadrant here. And what we want to do is find a pattern in the first quadrant that we can then generalize to each of the quadrants. So let me essentially draw in these key triangles that we were looking at, and I'm just going to draw the hypotenuse for each of these just so that we can remember what the angles are. So this one is an angle of 30, this one here would be 45, and this big one here would be 60 degrees. And we also do need to know them in terms of radians. This would be pi over 3, this one here is pi over 4, and this one here is pi over 6. So we want to know the x and y coordinates at each of these points, which we already found, and we also can extend this pattern to essentially an angle of 0 and an angle of 90 degrees. So remember, we found root 3 over 2 and 1/2 for an angle of 30 degrees, or pi over 6 radians. For a 60-degree angle, this was flipped. It was 1/2 and root 3 over 2 for x and y. And for this 45-degree angle, it was root 2 over 2 for both the x and the y coordinates. And remember, for these essentially key points, these extreme points, that the x and y coordinate here would just be 1 for x and 0 for y since it has no height, and that the x coordinate is essentially the same as the hypotenuse. And for this point up here, it's essentially the opposite. This triangle you can imagine forming from this straight vertical line would have an x coordinate of 0 and a y coordinate of 1, since the y coordinate is simply equal to the hypotenuse here. So we can find a pattern that essentially relates all of these numbers together. And so what I'm going to do is essentially rewrite all of these expressions, but put them over a denominator of root 4. And this might seem odd at first, but once I do it, you'll see that it actually makes sense and that there's a pattern we can find here. So now that I've drawn in all of these new expressions where the denominator is the square root of 4, then what I'm going to do next is essentially fill in a pattern. So let's start with the cosine values. The cosine starts at a value of 1. So this would be the square root of 4, since this should completely cancel out and make 1. And then the cosine values are going to count down. This will be the square root of 3. Let me redraw that a little bit nicer. This would be the square root of 2. This is the square root of 1 and the square root of 0. And then the sine function does the opposite. It counts upward. Starts at the square root of 0, then goes to the square root of 1, then root 2, then root 3, then root 4. And you can see that when you actually simplify all of these expressions, that they do simplify to these values in pink here. So this pattern does work, but in all honesty, this pattern, once I found this is the way that I remember these special angles for the trig functions. And once you feel comfortable about these special angles in the first quadrant, then generalizing them to essentially the second, third, and fourth quadrants is actually not that difficult. You just have to keep track of what your x and y values are and whether or not they're positive or negative. But essentially, just to get the general idea, a 30-degree angle here would have similar properties to if I drew an angle over here. Let me draw that a little bit nicer, where this angle is 30 degrees up from the x-axis. So over here, this would also be a pi over 6 above, but essentially we would have the same features. Since it would essentially be the same triangle, the only difference is that the x value would now be negative. So the x and y values would be minus root 3 over 2 and 1/2, since the y value is still positive.